Well, hello, I'm Eric Topol from Medscape, and this is the Medicine Machine, and I'm so glad to have my colleague, partner Abraham Verghese with me from Stanford. And today we have a rarefied chance, a privilege to discuss the whole pandemic story, the virus, vaccines, with one of the leading virologists, Dr. Angela Rasmussen. We're going to call her Angie because she's become our friend quickly. Welcome, Angie.
Thank you so much for having me, Eric. It's wonderful to be here.
Well, just a background, Angie was at Smith College before she had multiple degrees, primarily at the University of Washington and Columbia. And she's about to take on, in the new year, a new role. So maybe you can start with that, Angie.
Yeah, I'm really excited. I will actually be leaving the U.S. For the first time in my life. Well, not to travel, but in the first time in my career, and moving to Canada, where I will be starting a lab at Vito Intervac, which is a vaccine research institute on the University of Saskatchewan campus. So I'll be an associate professor at the university, as well as the research equivalent at Vito Intervac, studying emerging viruses and host responses, which is what I've been studying for the past 10 years or so. So I'm really excited about that.
Yeah, that's fantastic. Congratulations. I think
Thank you.
In some ways, you have been warming up for this pandemic unknowingly all your career, it seems like, right?
I really have. And there have been, a couple false starts where there were emerging viruses coming out that I worked on that we thought had pandemic potential. MERS coronavirus, H7N9 influenza, and Ebola, of course, although personally, I don't really think that one has pandemic potential, but there was obviously some significant outbreaks of those. So I've been prepared. I don't want to say waiting for this moment because I really haven't been. I would have been much happier if this had never occurred. But at least I feel that I'm used to seeing a new virus come out and rapidly switching my priorities around to start working on it.
Now, obviously this is moving at kind of unprecedented. The dynamics here are just crazy with, on the worst side, the public health response, particularly in the U.S., and then on the bright side, the vaccine trials, and they're getting finally out there. Where would you put us right now? What's kind of your overview?
I mean, I think we're still in a really bad place in terms of the vaccine availability. I'm very concerned not only about the supply of vaccines, but the willingness of the American people to take them. And I think that, going into the Christmas season, people are going to want to be spending more time with their families and their loved ones for the holidays. And we are, really at a place right now during the pandemic where we have more transmission than we've had before on a national scale. We're essentially having a 9/11 every day in terms of the number of deaths. Our hospital systems are becoming overburdened. And I think, we're going to be dealing with this for some time to come, even after people do get the vaccine, because certainly long COVID is a thing, and that's a very protean set of diseases, I think. And you would, know better about the cardiac consequences than I would. There's also consequences that are similar to ME/CFS or chronic fatigue syndrome. Those are debilitating conditions that can really last for years, decades. We may be looking at, an epidemic of disability and a loss of, sort of functional ability to live your life in many of the people who've had COVID. So this is a really bad place that we're in. And as much as I'm delighted and really overjoyed that we can sort of see the light at the end of the tunnel, a glimmer of it, thanks to these vaccines, I'm really concerned about how things are going to be as we get to that point.
May I just say that I've been so admiring of your tweets that I'm catching up on, because I think one of the challenges of science has been the communication gap between what people like and the degree of misinformation out there. And you've been really brave and very clear about not just how the virus works, but also what doesn't work, and calling out, the bad actors who seem to want to capitalize on this. Is that a surprise to you that you should wind up playing that role just as much as you're playing that hardcore scientist role?
A little bit. So at the very beginning of this pandemic, I had 250 Twitter followers. And I was feeling pretty frustrated because for the last 4.5 years, I've actually been commuting back and forth between New York and Seattle, where my family lives. So I was in Seattle when, in early March, when basically we realized I probably shouldn't get on a plane and go back to New York. And I was going to be staying home for some period of time. I wasn't sure how long it was going to be, but I thought I'd rather be with my family here in Seattle than by myself in my Manhattan apartment. And I felt really, helpless and to a certain degree because I wasn't in my lab. My lab was 3,000 miles away. I wasn't really able to do anything immediately to contribute to the response efforts. And so I thought, well, one thing I can do is try to break down some of these preprints and some of the news coverage that has been coming out, because even without putting the misinformation aside, early on, and I'm sure you both remember this, there were some really bad preprints that were getting a lot of press coverage. And it wasn't necessarily because people were intentionally spreading misinformation, but I think more because the public or the media didn't really know how to cover some of these topics. So there was the whole HIV, SARS coronavirus 2 hybrid paper that came out as a bioarchive preprint, and that sort of fed these smoldering conspiracy theories about this is a biological weapon, et cetera. So I just started explaining what those preprints actually say to the public. And as time has gone by, I've become more and more frustrated, which is why my tweets have become more and more frank and sometimes outright angry. But I think that it's really helpful, and the feedback that I've gotten is overwhelmingly positive, that people like to know what's going on. And my philosophy is really just that people are, well, first of all, my philosophy about public health is that you can't have it without the engagement of the public. And my philosophy about communication is that information really empowers people to decide for themselves. And I thought that that was one way that I could contribute until I got my data, my samples from my collaborators, and was actually able to start doing some work. So I'm a little surprised that I've gotten such a large following, but I'm really grateful for the privilege to be able to help in this space of communicating what people should take from all of the emerging research and what they probably shouldn't. And especially now that, one thing I was really surprised about was I didn't expect the US president to contribute to the misinformation the way that he has. And I didn't expect things to be this political with regard to the emerging science. But I feel that it really is a huge privilege to be able to try to dispel some of that confusion and misinformation and really put the power in the public's hands to do their part in ending the pandemic for good.
Yeah, well, that's what I got to know you so well about through Twitter, is telling it like it is. And I think that's why it's no surprise to me at all that you become a go-to for media and for the people that are wanting to know what's really going on out there. I think one of the first times I encountered, learning from you was about reinfections. And this is still a topic that is very much unresolved. That is, how many people are going to develop reinfections after having gotten through either the knowing it or not knowing it, but having developed some immune response, and then months later developing a reinfection. Can you explain why that is actually a difficult diagnosis to make, and what you think is really going on out there as far as reinfections after natural infection?
Yeah, so this is something I've thought about a lot, just because it really kind of gets back to one of the biggest problems of the pandemic, and that is actually logistics and sample availability, and to a degree, research funding. So one of the reasons why reinfections have been so difficult to study is that at least it doesn't look like a lot of them cause severe disease a second time around. Some of the reinfection cases that have been reported have resulted in somebody being hospitalized. But I think if this were happening at a really large scale, we wouldn't necessarily need to go back into all of these archival samples and see if people were coming to the hospital over and over again with COVID. So I think the prevalence is really unknown. And a big part of this is that to prove reinfection, you have to actually get samples from the first time a person was infected and sequence them, and then get samples from the second time they were infected and sequence those and compare the viral sequences to see if they're actually the same virus. And to a certain degree, maybe it doesn't matter if it's a huge clinical problem, if somebody is persistently infected, meaning they get sick, they still have the virus, but they don't know it, and then they get sick again, or if they actually get reinfected. But it doesn't look like that's happening very often, that we would have either persistent and then recrudescent symptoms, a return of symptoms with a persistent infection, or that somebody would be getting infected again. The problem, though, is that oftentimes samples that are collected, especially from early in the pandemic during an emergency, are not necessarily going to just be stuck in the freezer and banked so that you can go back and access them right away. So oftentimes you might suspect that somebody's been reinfected, but you won't actually be able to confirm that with a sample from their first infection. And that's in fact what we have seen with some of the earliest bona fide reported reinfection cases, that maybe they had samples to sequence from both times, but they won't necessarily get a serum sample from the first infection to see if they seroconverted, if they were, if they had antibodies, or if they developed antibodies after the first infection. So it really is a practical problem that, how should we be saving samples? Should we be consenting patients to use their samples for research? It's also an ethical issue, because you can't just keep somebody's samples around if they haven't given you permission to use them for scientific research. So it's really a problem of freezer space and having the foresight to collect some of these samples for potential downstream work. And that's very difficult to do during a pandemic. There are biorepositories set up at most major research hospitals, but even those, it's very difficult to get samples from them because everybody started working on COVID and everybody wants some of those samples. So to a certain degree, a lot of these unanswered questions could potentially be answered, but we just aren't collecting the right samples. We don't have funding. We aren't preparing to do the right experiments. So we kind of have to make do with whatever we have on hand. And that's not always adequate to answer some of these most pressing questions, including reinfection.
Before we get to the rest of this interview with Dr. Eric Topol and Dr. Abraham Verghese, a quick word from Medscape. Remember, this and every other episode of Medicine in the Machine has an accompanying transcript available at medscape.com, where you can also find an accompanying embedded media player, allowing you to listen along as you read. You can also subscribe to this podcast right there on our site, on Spotify, and wherever podcasts are found. Okay, now back to the interview.
And two other related to reinfection, two other questions. One is, the virus from the first infection could evolve. Is it hard to distinguish the evolution of the virus over time with a actual second infection? So even though the sequences are different, it could actually be just evolution?
Yeah, so that would be the situation in which you have a persistent infection where essentially symptoms are coming back. And that's actually not difficult to determine at all if you're able to sequence viruses from early on and then during the second infection. If you have the same virus, you might have additional new mutations, but it's unlikely that you would have completely different sets of mutations within that viral genome. If you have completely different sets of mutations, and people can also calculate this because we know what the mutation rate of the virus is. We now, thanks to initiatives like NextStrain, have a fair amount of sequence information, so we know what variants have emerged in different populations as well. You can go back and deduce and say there's no way that this virus could have been, could have evolved from this original virus in the first infection. Or you could say, this is consistent with the virus they had before. There's these new mutations, but that's to be expected. So we can confirm that this was intra-patient evolution rather than infection with two distinct viruses.
Okay, that's important. And then the other thing related to that is the infamous BSL BSL-3 lab that you know so well, that the medical community is not very experienced with. That is the work environment of introducing viruses and proving things. Can you tell us what it's like? Because you've done a lot of work in these labs.
Yeah, so most of the pathogens, the viruses that I work with are either BSL-3 or BSL-4, although if possible, we like to work at BSL-2 because it's just much easier. So there's 4 levels of containment. There's BSL-1, which is effectively working with things that aren't infectious at all. There's BSL-2, which is what most common pathogens. I did my PhD, for example, on rhinovirus, which causes most common colds. That's an example of a BSL-2 pathogen. It's something that can infect people, but it doesn't really cause severe disease. It's not a huge threat if it gets out, since rhinoviruses circulate every cold season in the human population. And you work in BSL-2, you have a lab coat, you have eye protection, you work on viruses and cells in a biosafety cabinet, which is basically a hood that has airflow inside that keeps the virus from coming out. But this is what you see when you see pictures usually of people working in a lab. They're working in BSL-2 conditions. BSL-3 is 1 level up. So BSL-3 is what you would work on SARS coronavirus 2 in. Other pathogens that may not be select agents, or they may be as well. SARS, for example, SARS coronavirus classic is a BSL-3 select agent, which means that the US government regulates it more tightly because of its potential to be used as a biological weapon, or its potential to be a threat to national security. And in BSL-3, it really kind of depends on the pathogen that you're working with, what types of protective equipment you wear. But in general, you'll either wear a PAPR, which is basically a powered respirator, or you'll wear an N95 respirator and eye protection. You'll usually wear either a Tyvek suit or some kind of protection for your body. And there's usually also controlled entry and controlled engineering controls. So there will be an autoclave for disinfecting used disposables, for example, before they ever come out. There sometimes is a dunk tank where you will dunk something in disinfectant according to a validated protocol before going out. And then, those are more tightly regulated, obviously, because they're pathogens that do have the potential to cause epidemic disease and often have a higher mortality rate, or they can cause more severe disease. They may not have a vaccine or treatment available for them. And then the highest level of containment is BSL-4. This is what you work on Ebola in, for example. Most select agents are BSL-4 pathogens. That's what you're used to seeing with the spacesuits. So people wear a positive pressure spacesuit, which actually hooks up to an air supply and inflates the suit. So that way, even if you get a tear in the suit, air will be blowing out of it, so pathogens can't go into it. Yeah. That's the kind of situation also where when you go in, basically once something goes in, other than the people working in there, it doesn't come back out. So if you take an animal in there, you euthanize the animal inside the BSL-4 facility so that they can't come out with any pathogens that you're working on in there. If you're taking samples out, you have to be very, very rigorous about your disinfection protocols. You can dunk things out, which is basically there's these dunk tanks where there's a bunch of disinfectant in them. You put tubes or whatever in there, and then you have to shower out in a chemical disinfectant shower. And then after a certain amount of time, you can come on the other side outside of the BSL-4 and remove those tubes, and they've been disinfected. So you're really not taking anything out. Inventory is extremely strict in a BSL-4. Again, most BSL-4 pathogens are considered select agents. So you have to be inspected by the US government every year. Any kind of violation of how you're maintaining that inventory is a violation of federal law. You have to really account for every single last thing that you bring in there, and especially your virus stocks. So as I mentioned, most of the things I work with are BSL-3 or BSL-4, and there's not a lot of these labs because of the huge burden of just maintaining them and make sure that you're working within them safely in a way that doesn't endanger the public and also is not a threat to essentially national security or defense.
Well, it's a brave crew of virologists in the BSL-3 and 4 world. Abraham, over to you.
Yeah, I was fascinated that you've done work on chronic fatigue, which I think we'll all agree is a difficult disease to agree on. You know, we have clinical criteria and the immunological profile is so varied. So this might be the first time that we have a pathogen that truly seems to lead to a state that resembles chronic fatigue. Is it in fact the same syndrome that is being triggered? And what is it about this virus? What is it? What does a virus have to do to become a putative cause for chronic fatigue type syndrome, myalgic encephalitis?
So that's a great question, Abraham. And to be honest, I really don't know the answer. Going back to the 1918 pandemic, there was a consequence of that was called encephalitis, which sounds an awful lot like ME/CFS. I think that maybe chronic fatigue syndrome, ME/CFS is, well, I mean, it does seem to me that it actually refers to a collection of different syndromes. So some people have, gastrointestinal involvement. Some people can trace it to a time that they had some type of pathogen that they couldn't put a finger on, and other people have no known idea where it came from. It seems like it probably is more than just all people have the same diagnosis even before this pandemic. Whether or not people with so-called long COVID have ME/CFS, it sure sounds like some of them do, and I would defer to clinicians who are actually diagnosing ME/CFS to say whether or not they meet those same diagnostic criteria. But I think this may be, since it's the first time we've really had a pandemic with such broad effects on people's different organ systems, including these neurological effects, this may be an opportunity that we should really take to try to understand how any viral infection, acute viral infection, can cause these really complex syndromic long-term diseases like ME/CFS. But the bottom line is, I don't really know if this is the same as people who get ME/CFS in other situations or from other causes. I mean, it's always been thought, and I haven't worked on ME/CFS extensively. I have sat on a panel that at NIH that was actually, I was invited to be on it because I don't work on ME/CFS, so I wasn't a stakeholder, and therefore I could make objective recommendations to NIH on how they should direct their funding. But knowing, what little I do know about it, it seems like the etiology of it has been a constant question. And this may be an opportunity for us to get on top of that and start addressing some of those questions in real time. So I'm really pleased to see, and not just because, long COVID seems like it is really debilitating and difficult for patients. So I'm pleased to see for that reason that there are all these long COVID research centers popping up. But I hope that some of that research can really address some of the questions that you just asked about the relationship between viral infection and ME/CFS.
I should ask both of you, because Eric to me is, really on top of this more than most infectious disease people I know. Is there a correlation between long COVID and the nature of the severity of the illness or the particular immunological profile of that person's illness? Have there been any ways that we can predict who's going to get long COVID?
I have not seen any studies that characterize like immunological markers of long COVID. There really haven't been a lot of studies about it, period. I mean, a lot of the stuff that I've heard about it has really been reporting in the mainstream press, or hearing from patients themselves directly. People have started to characterize case studies of what I think people now are recognizing as long COVID. But I don't think we can really say with certainty who's going to get it or not. One thing that I have seen, though, is that it doesn't appear to be correlated with disease severity.
Right.
There are reports of people with severe COVID who develop long COVID symptoms, as well as people who said that they had mild disease and never really recovered from it.
Yes.
So I think that makes it even harder to predict, because if you have mild disease and it's just like a cold and you're recovering from home, you're unlikely to go have your blood drawn and do serum cytokine profiling, for example. You may be less likely to contribute samples during your acute illness to a biorepository where they could then be studied. So I think it's a tremendous problem in trying to get to the bottom of it, what the risk factors for that actually are.
Yeah, from what I've seen, totally, you summarize it well, Angie. The people who are younger, who have more mild infections, and also females, all of those are factors that are increasing the risk, as opposed to what Abraham was trying to point out, that you would have thought before all this started that it might have tracked with severity, and it's just the opposite. Yeah. I wanted to get into this topic that's really fascinating, which is, and debated, surfaces. Well, you've obviously watched all the mask and aerosol and those, but there still is a fomite surface looming controversy. And that also brings in this BSL-3 and culturing the virus and all this stuff. Can you tell us what is the scoop on surfaces? Can you get
This is one of
COVID
those
from
things.
surfaces? Yeah.
Yeah, probably. I think you probably can. I think one of the real problems here is that, and this is one thing that I think has been really difficult to communicate to the public in general, is that a lot of what you would think are basic questions about this virus. So what's the primary route of transmission? How long does the virus remain infectious? How many infectious viruses do you have to be exposed to in order to actually become infected? What are the variables determining that? Why can't we just look at all of these, super spreading events or these epidemiological reports and just figure it out? And the reality is that in the real world, you often have, it's rare to get a well-designed natural experiment, or it's rare to have all the pieces fall into place. So what we do know is that depending on environmental conditions, the virus can certainly remain infectious on surfaces for periods of time that can last hours to sometimes days. Depending on the temperature, in laboratory conditions, again, it can last for potentially weeks. But is that the case in the real world? Well, usually when people do environmental sampling, they're using PCR to detect the virus, which doesn't look for infectious virus. That only looks for RNA. Further complicating things, and I think people who are not virologists don't always appreciate this, viruses themselves, and especially RNA viruses like coronaviruses, make all kinds of mistakes. So any infected cell will produce a bunch of different virus particles called virions, but not all of those are actually infectious. They may have a defective genome packaged inside them. They may not have a genome at all inside them. They may be what's called a virus-like particle. And so we measure that by something called the particle to PFU ratio. And some people now are using the RNA to PFU ratio. PFU is a plaque forming unit. That's how we determine if a virus is actually infectious. And how we do that is in a BSL-3 lab, you take your sample, you put it onto a layer of cultured cells on the bottom of a plate, and then you put a semi-solid overlay, so basically agar or jello, on top of that. And then you culture it for a few days. And after a while, any place that an infectious virus landed will start to kill the cells. So it's called cytopathic effect, or CPE. When you get enough cells in that one spot that die, you can take that overlay off. You can use a dye to color the cells that remain. And wherever there's cells that had died, there will be an empty spot. And we call that a plaque. And you can count the plaques. And if you serially dilute this using 10-fold dilution series, you can go back, you can calculate back up those dilutions and figure out how many infectious units per milliliter or whatever unit of volume you're using you have. So that's how we determine if something's infectious. Usually there's a large particle to PFU ratio, meaning that there are a lot more particles than there are of these plaque forming units or infectious units. So I think that makes it really challenging when you're trying to look at how much infectious virus is on a surface in the real world using PCR, because you can't really tell that. And the other issue is that, unlike in laboratory conditions, if you're trying to culture virus off of an elevator button, for example, or a doorknob, people are touching that, but they're getting all kinds of other stuff on there too. And remember, I said the plaque assay has to be done on cultured cells. If you get bacteria, if you get yeast in there, they're going to overgrow that, and you're not going to be able to calculate how many plaque-forming units you have. So it makes testing for infectious virus in real world conditions very difficult. But that said, I think that the evidence is pretty clear that the majority of transmission is probably by either aerosols or droplets through close contact. I think it's also very difficult, and this has been somewhat controversial for reasons that I don't completely understand. It's very difficult to separate how much of that is aerosol transmission and how much of that is droplet transmission. How much are you breathing in, and how much just has to do with the fact that you're in really close contact with somebody. They may be, exhaling and coughing droplets on your hands, and then you touch your nose and become infected. How do you distinguish those two things? Because the aerosol transmission that's occurring is also short range aerosol transmission that is from you being, again, close to somebody. So it's really hard to separate that in the real world. But that said, just because those are probably the primary modes of transmission doesn't mean that fomite transmission doesn't occur. There's at least one case report of fomite transmission occurring in China, or probable fomite transmission, in which a man was blowing his nose into his hands and touched an elevator button, and then somebody who got into the same elevator and touched the button became infected. And they speculated that it was likely fomite transmission. But again, it's really hard to say in the real world without a way to confirm this by culturing virus in the moment, which most epidemiologists are not prepared to do, since again, you have to do all of this in a BSL-3 lab. It makes it really difficult to get to the bottom of this question. So what I usually tell people is that, my suspicion and what the data does support is that most transmission occurs via aerosols or close contact via droplets, and some unknown smaller proportion of transmission probably occurs by fomites, but it has to be in the right situation. I completely agree that we've gone overboard with surface disinfection, as I know you were commenting on, Eric, on Twitter, and that article by Charles Haas and Lindsay Marr and Joseph Allen showed. I agree with that. I think that we shouldn't be, bleaching everything in sight and disinfecting our produce and our groceries and our mail and so forth. But we should still do good hand hygiene. We should still emphasize that. We should probably disinfect common high touch surfaces as well, such as doorknobs to like an office building. But I think that that's probably where we can limit that. We shouldn't be recommending disinfection, especially at the expense of taking other measures to reduce virus in the air.
No, that's great summary. Again, the absence of evidence is not the evidence of absence. And, there's a few of these cases, like in New Zealand with an elevator button and a trash lid, and the one you mentioned in China. But overall, it's so hard to make the diagnosis, the confirmation that there may be many others that we just don't have proof. Now, I want to hand it back over to Abraham again, but I had one other question that I thought was really, you have unique perspective. Here you are, you work in these BSL 3 and 4 labs, you have all this gear on, and then you must walk around at times or drive around and you see people with nothing, naked as far as protection. What are your thoughts when you know what it takes to protect about the virus? Because you have a whole different perspective than the average person by far.
Right. Well, I don't think people need, even for a virus that's normally used under BSL-3 laboratory conditions, I think in the real world, it's certainly not necessary for everybody to be running around in a PAPR. And, that would, the PAPR is the thing that you see when people are showing people in the hospital or the lab, that it kind of looks like a big clear hood and it has a tube going down to the back where the motor attaches to your belt. I don't think that that's necessary. And I honestly don't even know how valuable it is for everybody to wear an N95 mask, for example, because N95 respirators have to be fitted to your face. And every year you have to go take a fit test, which basically involves throwing a sheet of plastic over your head while you're wearing an N95 and spraying a chemical that you can taste. It tastes bitter or sweet. And if you're inhaling that through the mask, then your mask is not fitting correctly and you will experience that. So I think that trying to fit test people nationally is kind of ridiculous, because the other thing is, in the BSL-3 lab, you're growing virus in culture, and you're probably dealing with much higher infectious titers than people are going to be exposed to in the real world. But that said, it's very frustrating to go out in public and see people not wearing masks, intentionally wearing masks incorrectly, intentionally refusing to wear masks, or giving people a lot of attitude if they're asked to put their mask back over their nose, for example, if they're just wearing it over their mouth or over their chin. It's very frustrating, because I know a lot of that is not based on science or concern for others. It's been very frustrating, I think, to convince people that they should wear masks for the good of their community and not necessarily themselves. It's been really just frustrating to try to communicate that masks are not perfect. They don't provide complete protection, but that doesn't mean that they're useless either. In the real world, there's all sorts of variables that it's impossible to really model or test in the lab. So my feeling is that if risk reduction is additive, if all of these measures, masks and social distancing and ventilation, they all add up to create the most exposure reduction possible, you should try to implement as many of those as possible. But because it's been so politicized, I think it's been very, very frustrating to try to convince people that this is something they should do.
Right.
I wanted to sort of ask a question about testing, and that is, should we be reporting our PCR testing differently than just positive, negative? Should there be an attempt to sort of get into the degree of positivity, if you would? And secondly, a question about the saliva test that's just, making its way through for home testing. Your thoughts on that would be helpful.
Yeah, so I think that's one of the biggest questions that I've had through this pandemic, is the role of testing and how it's being reported. And honestly, I was shocked over the summer when I was talking to Apoorva Mandavili from the New York Times, and she told me that they actually don't report CT values, which is the numeric value that the PCR test produces that correlates to how much virus you have. I understand why they don't, because these tests have all been given an emergency use authorization. So my understanding is that you can't include the CT value in the patient's electronic medical record, but the doctors do get the results of the CT tests or the CT values in some cases. And they will make clinical decisions based on that, but it can't go in the patient's medical records. At least that was the case at Columbia. And that's what the head of our clinical pathology lab explained to me. I think that is missing information. I think it would be helpful to have more information, but even that discussion has gotten very confusing, I think, in the public eye. So now we've heard, oh, well, any PCR test with a CT value above 35, some people say 30, should be considered actually a negative test. And it's a false positive. And that's not really true. So first of all, there's different PCR tests. And depending on whether you're running that on a Roche instrument or some other manufacturer, you might have a different number of overall cycles in the PCR test, which is what the CT stands for. That's the PCR cycle at which the fluorescence that's detected by the test exceeds a certain threshold. So the earlier the cycle, the more starting material you had to reach that threshold. So if you're running a 40 cycle PCR test and you have a CT value of 35, sure, that's not very much virus. If you have a 35 cycle PCR test, that's even less virus if you're at CT 35, but it's not as little virus as if you were running a 40 or 45 cycle test. So there's some discrepancies between the different tests that are being used that make that information complicated, at least when it comes to trying to look at results in a standardized way across all these different tests. And the other issue with that, with calling those false positives, is that, sure, if you're testing people who have already recovered from COVID and they're getting these consistently high CT values, yeah, that's probably not infectious virus. But if you're testing somebody where it's unknown if they've had COVID or not, you could be detecting very low levels of viral RNA early on infection, and those levels are going to go up, and that person's suddenly going to become a transmission risk. So it's really, if we're not able to test people longitudinally, repeatedly, it's really hard to make decisions about what is a CT value that counts and which is not. All of that said, with regards to the saliva test or any type of at-home testing, I think that definitely has a place, because one thing that we do need is to increase our testing capacity still. We've needed this since the beginning of the pandemic. I think that anything that can help people make decisions about how they should behave, whether they should go to work, whether they should go meet up with somebody who may be high risk, I think that is a generally good thing. I think that what's going to be key is presenting it to people in the right context. So somebody should know what to do, for example, if they get a positive test that they've done at home. It should be more like a pregnancy test, where I think if people take a pregnancy test and they test positive, they're not going to say, okay, well, back to my normal life. They're probably going to call their doctor and get that confirmed and see what they need to do in terms of prenatal care and planning for the new arrival. I think that people now may not know what to do if they get a positive COVID test. They might say, well, I feel fine, because most people are not as well versed as I am at the dangers of pre-symptomatic transmission, or that any of us who are working within, a scientific or medical space, we've all become acutely aware of the likelihood of pre-symptomatic transmission. But I think a lot of people still don't really know this. And they may say, well, I tested positive, but I feel okay. If I start to feel sick, then I'll go home, or then I'll isolate. And without that kind of guidance and that, a consistent message about what people should be doing if they test positive at home, I think that it could potentially be really dangerous to put tests in the hands of everybody. But I think that's an easy barrier to overcome too, because if we put out rapid at-home tests, we made a robust reporting structure, we made really key, easy to understand, actionable steps that people should take if they do test positive, I think that could be really powerful in terms of people being able to involve themselves in the efforts to reduce community transmission.
And the saliva, do you want to comment about, is that as good as anterior nares?
So this is something that I think is to be decided for every test in general. And I'm not sure which saliva test you're referring to. So saliva tests for PCR, like the Saliva Direct test that was developed at Yale, for example, is actually more sensitive than anterior nares or nasopharyngeal swabs. For antigen tests, though, I'm not sure if that's the saliva test we're talking about.
Right.
For antigen tests, they're generally less sensitive, period, than PCR tests.
Yeah.
And what has been proposed, notably by Michael Mina, who is at Harvard, who is the really most vocal advocate for rapid at-home antigen testing, he's really an evangelist for it, has made the argument, which I agree with, that it could be really helpful in helping determine who is positive when they take that test. Because even if it's not going to pick up those people who are really early on in infection or people who are really late and are probably not shedding infectious virus any longer, if they are shedding enough virus to transmit it to others, they would test positive with those tests. I think that in that context, those could be tremendously useful. I think the real challenge is communicating that to people and what a positive test means, that means you're contagious now, whether you feel sick or not. And that means you should immediately isolate.
I had a question on the fortune of having these very powerful vaccines, at least the mRNAs and perhaps others that will come along, in that being spike protein directed, and that it really was so potent. The question is, do you think that with all your other anchoring with pathogens, the next pandemic, what might we not be so fortunate? That is, this was potentially easy target, this virus, even though it's been a wreck of the world. But what is your sense going forward? We're going to have more pandemics. We're going to have more viral pathogens. Are we just lucky? I know that's a hard word to use with this, but, or you think that we'll always be able to come up with a way to quash a pathogen?
Well, I think I agree with you that we were lucky, not because this pandemic occurred, but because it did occur with a beta coronavirus that we've already seen a relative of before. And already there were mRNA vaccines in development for MERS coronavirus. So we understood the basis for which neutralizing antibodies, for example, work to stop beta coronavirus infection. And it was just a matter of basically swapping in the spike protein of SARS coronavirus 2 for the spike protein of MERS coronavirus, which was already in development at Moderna, for example. I think that there will be a next pandemic, and I hope that it is with a virus that we already have developed some vaccines to, but there is the possibility that it could be something completely new. And there are at least 25 different virus families that are capable of being human pathogens. I think it is possible that we might see a pandemic emerge with a virus that we really don't know much about at all. The solution to this is, I think this is a wonderful test for vaccine platforms like the mRNA vaccine platforms, as well as the viral vectored platforms. There was a viral vectored vaccine made with the vesicular stomatitis virus that actually was stuck in preclinical development for 10 years before the West African Ebola outbreak. And that vaccine is incredibly effective. So, it really produces sterilizing immunity to the point where I've been involved in host response studies in non-human primates that were challenged with it after vaccination with that vaccine. And you can detect any sort of host response after challenge, which suggests that the immunity is so robust that the animals don't get infected at all, even an abortive infection. So we have these vaccine platforms now that can be rapidly changed out for other viruses. I think what we need to do is start understanding all of these different virus families, assuming that we won't know the individual virus that emerges. We should put some effort into trying to predict which ones might emerge, but we also need to put some effort into looking at prototypic viruses from these families, using animal models, experimental model systems, so we understand the basis for protective immunity for these other viruses and these other families. If something came out like, the movie Contagion was based on Nipah virus, which fortunately has not become a human pathogen. Nipah is a paramyxovirus, and we know a lot about paramyxoviruses, but it's a pretty diverse virus family. We should be spending more time working on other viruses within families like that, in case one day a Nipah variant comes out, or a virus that we haven't seen before that's like Nipah, which can be transmitted by the respiratory route, comes out that is more transmissible from person to person. Yeah. We need to be able to rapidly develop vaccines that are likely to be effective so that we don't even have to go through the process that we've gone through, which has been amazing. It's been so fast compared to other vaccines, but we really need to have some flexibility about getting these vaccines out, making them rapidly, and starting to distribute them so that something like this never happens again.
And also that we're fortunate that this isn't a rapidly evolving virus, making it even more challenging for vaccines. You are an amazing resource. I nominate you for the Coronavirus and Pandemic Preparatory Task Forces of the Future. Really, Angie, you're a phenom.
Well, thank you so much.
Let me turn it back to Abraham. We're going to wrap it up here, but this is, I go on all day. I'm just learning so much here. Abraham, what do you?
Yeah, me too. I just want to say, please keep up your effort, your voice. I think countering the misinformation, the blurring between fact and opinion is so strong that we keep needing to have people like you underline the facts as opposed to the opinions. And thank you for that.
Well, thank you so much, both of you. And I do plan to continue my public outreach activities, which at this point has sort of become a second job. Although I'm hoping to take the next couple weeks kind of off, just because I feel like I haven't had a break in a year. But my next position, as I mentioned, in Canada, is going to be working at a vaccine institute, and that's really what I hope to do, is to start addressing questions like this about the next pandemic. And I'm a really firm believer in the value of interdisciplinary work. I think that to counter the next pandemic, you're going to need virologists like me who have, subject matter expertise in how viruses work, how immune responses work. But you're also going to need people to appreciate this at the policy making level so that it can fund this type of interdisciplinary work. You're also going to need epidemiologists to understand how these viruses are likely to spread. You need vaccinologists who can get down into the nitty gritty of making an actual vaccine. You need anthropologists and sociologists to get people to take those vaccines. So this is really going to be a huge, I think, global effort. And I really hope that going forward, we appreciate the importance of having people from multiple disciplines all at the table. Because that's the only way that we're really going to be successful at this moving forward, and especially globally.
Well, having you at the table, that's key, because you're, just a great educator, no less, the experience, and you're young, so your contributions going forward. Oh my gosh, watch out for Dr. Rasmussen in the decades ahead. My goodness. So thank you so much for joining us. We'll have to check in with you again over time, because this is obviously, we've got this with us for some time, and we may need to do some further alignment with you in the months ahead, but really appreciate your coming and joining us today.
Thank you.
Well, thank you so much. It was really a pleasure, and I'm happy to come back anytime. Really, you've been such a critical voice too, Eric, and it's been really helpful to me trying to deal with the real deluge of information that comes out all the time. You seem to have a knack for picking out the little needle in the haystack that really should be at the top of the pile. So right
Amen.
Back at you. You've been incredibly helpful, a really important voice in this pandemic. And I'm grateful. I'm not grateful for the pandemic, but I'm grateful about meeting people like you. I've met more people outside of my own discipline this year than I ever have. And it's been really tremendous, and it makes me optimistic going forward. So thanks for the opportunity to chat with you and to meet you.
And that's it for this episode of Medicine and the Machine. Medicine and the Machine is produced by Medscape editor Robbie Atuma. I'm your audio engineer and audio editor and a voice here at Medscape. The hosts of this show are Dr. Eric Topol and Dr. Abraham Verghese. Remember, there's a transcript of this episode available at medscape.com. You're listening to Medicine and the Machine.